Okay, welcome back. It was a bit of a heavy session before coffee, but I hope you got the idea of what the game that is being played is. Okay, and say this afternoon there's a couple of paper exercises. Perhaps some of those formulae in the original derivation went through. I didn't do step by step, but I think it's important that that exponential solution of the basic iconal equation is one that is quite easy to understand from your basic mathematics. So I think it'd be nice to make sure you understand that one. Okay, in this second half I want to extend these methods. We've got this idea now that if we've got more than one body, so if we've got a composite object, that what arises is a rather simple mathematical structure where the S matrices that describe the individual particles scattering from the target can be combined in simple products to produce the effects for more complicated objects. All right, and I want to, in this up to lunch, I want to talk about an application of these ideas to a set of reactions which are being used extensively at fragmentation facilities, namely knockout reactions where particles are removed from a fast beam. You don't measure very much, so you've got rather inclusive processes. And so this is a slightly different situation to what you encounter when you've been doing coupled channels calculations before, for instance. Okay, so that's the motivation. So this is the plan. Okay, so there'll be more pictures here in terms of there'll be some equations to relate us back to last week's stuff and overlaps, and to show that with certain approximations the same ideas carry through for these sort of reactions. But I say I'll show you some pictures, some cartoons of various things that are happening to try and give you an idea of what we think is happening in this particular set of reactions and why they may be able to be described in a reasonable way using the formalism that I've put before you so far. Okay, so I want to introduce knockout reactions, show how they can be calculated from, first of all, just a simple bound state, and convince you that what's involved is the overlap function, just as we had last week. I want to discuss momentum distributions, and we'll define what those are in a moment, and how the shape of these momentum distributions can be used to say something about the wave function, the state of the nucleon that was removed in the knockout reaction. Okay, so this is heading towards spectroscopy. Okay, we can measure the final state. We get a distribution of momenta, and by looking at that, we can figure out that the removed nucleon was in an S state relative to the core and a P state, D state, whatever. Okay, and also want to discuss a bit more. We need these potentials in order to calculate an S matrix. We need a potential. And now we're talking about the potential between, say, think of an exotic particle of your choice, oxygen 23, say, oxygen 23, neutron-rich oxygen isotope interacting with beryllium-9. Okay, so we can think of that as a neutron and an oxygen 22, and so I need an optical potential for oxygen 22 on beryllium-9 at, say, 100 MeV per nucleon. Okay, you are not going to find that on the database. Okay, these things have not been measured. So if we're going to deduce optical potentials for these things to compute a realistic S matrix, we need some theoretical input in terms of the densities of these objects, calculated once again with our Hartree-Fock method, and some effective interaction, and using a folding model so that we can construct the optical potential in a rather general theoretical way and build in the correct densities and properties of the NN force and such like. Okay, so we're entering a region where we're doing reactions with systems that we usually don't know the interactions for, and so we need to put some theory into constructing the optical potentials in order, once we calculate the optical potentials, then I can calculate an S, and then I can go forward and calculate the reaction. Okay, so it looks all very simple. We need realistic S matrices, but they don't come for free. And I say very often we're now dealing with exotic systems for which we simply don't know what the optical potentials are from measurement. Okay, so the last thing you want to do today, well, what you should be able to do once we've done the lectures today, is that you should be able to go away and compare some published results for taking a neutron out of beryllium-11, for instance, and understanding what the nature of the halo state, the last bound neutron in beryllium-11 is, or doing the same thing for carbon-15, or for any other nucleus of your choice. Okay, so I want to go through an example and show you how we can make reasonable choices to do such things. Okay, so this is the cartoon, first one. Okay, I showed it before. So here's the picture. We've got a projectile. I'm starting to introduce the notation we had last Tuesday, if you remember. We had a composite nucleus, which we had spin A. One particle, there's a mechanism which removes one particle from A and leaves a nucleus with spin B. Okay, so we might call this particle 1, this a core, this a valence particle, this a core, it's up to us. May call this A, we call this B. Okay, various notations. But if you remember last time, if we had A and B, and if we were using independent particle models, we had some equations that allowed us to determine the spectroscopic factors in terms of coefficients of parentage. And if this nucleon that's being removed is in a state J, and there are 6 nucleons in that state, we learnt some rules as to what the spectroscopic factor had to be and such like. Okay, so we'll be returning to those today, because what we're doing is a reaction where we start with a composite nucleus, we're going to remove one nucleon, and so we're going to be talking exactly the sort of same language as we had last Tuesday. Okay, so there's the composite nucleus. There is a target, carbon-12, beryllium-9, something light, so the Coulomb effects are very, very weak. This is fast, 100 MeV per nucleon, as we saw a moment ago, is about 40% of the speed of light. And this comes in, and what you observe is that this object, let's call it the core, or B, is seen to be travelling after the reaction in a forward direction, namely the projectile is seen to have lost one nucleon. And you see this guy going forward, and you can measure its energy and measure its momentum, and if it happens to be excited, it may emit a gamma ray, and if you see the gamma ray, you learn something about the state that this object was left in. Okay, so but the experiments don't measure anything about this. Okay, so this might be excited, it might be completely disintegrated. If this nucleon is coming in with 100 MeV per nucleon, and this nucleon strikes carbon-12 with 100 MeV, the chances are all sorts of things happen to carbon-12. Okay, so this is a rather inclusive process. So we want the cross-section for this coming in, observing that going out, irrelevant of anything else that has happened. Okay. So, question again, how do we describe such a collision, such a reaction channel, and what can we learn if we measure these limited number of things? Okay, well this is an example which, I say, it's just here an example to give you a flavour. Okay, so here's an example of a set of data where carbon-17 is incident on a beryllium-9 target. Okay, carbon-17 interacts with the beryllium-9 target, and carbon-16 residues are seen to be going on forward. Okay? Carbon-17 goes in, a neutron gets taken out somehow, and carbon-16 goes forward. And one can observe gamma rays from the carbon-16, and you can also measure the momentum of the fragments, either in coincidence with the gamma ray, or if there was no gamma ray, the momentum distribution of the fragments without a gamma ray. Okay? And this is an example that shows you the momentum of those fragments, those without a gamma ray, which one assumes are associated with populating the ground state of carbon-16. Those with a, what's this one, 1.77 MeV gamma ray. This is the momentum distribution of carbon-16 fragments associated with a gamma ray from here. So this looks like the momentum distribution of fragments left in the 2+ state. And then there's 3 closely spaced states which you can't resolve. But this is the momentum distribution associated with gamma rays, unresolved gamma rays with whatever that number is minus that one. Okay? Okay. But I say all I want you to take away from this is that these distributions have different shapes. Okay? So they're telling us something distinct about the mechanism in which a neutron was removed, leaving carbon-6 ground state. This one has a different shape. And you can see this one shape is different, but you can obtain that shape by adding a bit that looks like this, plus something narrower. Okay? And similarly, this one up here doesn't look like that, but it also looks like something like that, plus an extra little narrow bit. Okay? And what we'll see in working through what we're going to do now is that these shapes are characteristic of the angular momentum of the state of the nucleon from which the particle was removed. Okay? So that shape there is what you would expect theoretically if the nucleon was in a d state. And so this one says it's mostly d state, but there's a little bit of s state. Okay, and this one says it's mostly d state, but there's a little bit of s state there. Okay, so in other words, it's telling us information about the orbital angular momentum content and the states occupied by nucleons in the carbon-17 nucleus, which are removed in this process. Okay, so this is the sense in which, by measuring the momentum of the fragments and looking for gamma rays, you can start to understand something about the structure of these exotic systems. Okay, so the other thing, let me remind you of, is that because we're talking, usually when we talk about radioactive beams and fragmentation, we're talking about asymmetric nuclei, nuclei which have either a large neutron excess or a neutron deficiency. Here's an example, for instance, with silicon-38. Okay, so normal silicon lives around 28 with 14 neutrons and 14 protons. Here there are 24 neutrons. Okay, and I want to show you this primarily to advertise DENS again. You've got DENS, right? DENS does a Hartree-Fock calculation for you. And if you haven't got a clue about silicon-38, which I don't, the first step for me is to say, what does the Hartree-Fock tell me? What does the mean field tell me this nucleus with 24 neutrons and 14 protons look like? Okay? So running DENS, I can go away and calculate the neutron and proton densities from these guys. Okay? Experimentally, the neutron separation energy of a neutron from this system is 5 MeV, because there's lots of neutrons and they fill up near the Fermi surface. The separation energy of a proton from this system is 20 MeV. Okay? So the protons are very well bound. Okay? And so these are experimental numbers. And this is what the Hartree-Fock calculation gives here. Okay? So I just invite you to look. I don't know if you can see, but it says in the Hartree-Fock, the neutrons fill up the single particle states up to the F7 halves level. Okay, so you fill the 20 magic shell, the magic number at 20 of neutrons, and there's 4 left over, so there's 4 neutrons in the F7 halves. Okay, and the protons fill up this orbit to the D5 halves. It's got 14, and so that's exactly enough neutrons just to fill up the D5 halves with 6 particles in it. Okay, so I say what I'd like you to take away from here is this is experimental number. The Hartree-Fock says that these protons are expected to be bound by just above 20 MeV. It's remarkably good. Okay, and it says that the neutron, the last bound neutron here, that's about 3, saying about 3 MeV. Okay, and it's not right. But I say if you want to gain a first impression about what these nuclei are doing, this tool that you've got here in terms of DENS is a very simple way of getting accustomed with a nucleus like this, which you might want to think about studying. Okay? And these are the neutron and proton densities, and because of the neutron excess, you can see how the neutron extends into the surface and has a longer range. The neutrons have to go somewhere, and so the neutrons are sitting at the surface because the neutrons are much less weakly bound here. Okay, so their wave functions extend further in the distance because of this weak binding. The least bound proton is bound by 20 MeV. Okay, so this is a feature of asymmetric nuclei. Okay, so one thing you might want to do, use these knockout reactions for, is that if you fire silicon-38 at a beryllium-9 target and you look for silicon-37 coming out, you will primarily probe these most weakly bound neutrons near this Fermi surface. Okay? So you'll be able to check from the momentum distributions if they really look like neutrons having been pulled out of F7 house. Okay? And similarly, the cross-section for removing these guys will be smaller, clearly, because these are much more tightly bound. But you can also look for, once you take a neutron out, a proton out of silicon, what do we get? 13? Aluminium? Aluminium? What's got 13 protons? Aluminium? So that would be aluminium-37, right? So if I look for aluminium-37 products coming in forward directions, it means I'll have removed a well-bound proton bound by about 20 MeV, and we'll be able to see from the momentum distribution whether, in fact, these are consistent with d5 half particles. So if we want to examine whether these mean field orbitals, whether they're changing order, you've heard, presumably, as you've gone through life and sitting in meetings, that traditional shell closures are being destroyed and levels are inverting. We had an example this week where there's a level inversion in beryllium, neutron-rich beryllium, and etc. So one way of asking whether these levels are really what we think they are in the right order would be to do such a reaction as this. Yeah.
How well is the approximation assuming a spherical?
How good is it? Well, that's another good question. Yeah. Yeah.
Because we will not have
For some systems, the assumption that it's spherical will be very good. For other systems, it'll be terrible. Okay, but in this system, what I'm showing you is that I say it's a philosophy. Okay, if you're dealing with a system that you don't know anything about, and there's very little data in the literature, one way of doing this is to take some very general theoretical tools, and a mean field model gives you a first picture of what this nucleus looks like. It'll give you some predictions, and then you can look at experiment and say, is there something crazy going on here, or whether we a first order picture in my head about what is happening in this system. That's all I'm advocating, okay? That you collect, that's what I have done over the years, collect a set of tools which I sort of trust and some I doubt, and you build a little library of things so that when you encounter a new bit of physics, you run them through your tools and you see whether you can picture some sort of coherent picture in your head of what is going on here, from which to build a model to model the process. Okay? So you're right. This is a spherical calculation. If you're in a system where you're most certainly deformed, then you should go and ask somebody else for a deformed Hartree-Fock code or whatever. Okay? But I just want to make this picture clear. We have a spatial domain where things are happening, where density is happening, and then we have an energy domain. Okay? And these reflect one on the other, and what you're seeing over here is a result of this and vice versa. Okay, so what is happening? So this is the other cartoon. We'll get onto the equations in a moment. Okay, so what we've got is a projectile which contains various nucleons in various states. Some are more tightly bound, and so their wave functions will decay away quicker. Some are less bound, and so their wave functions extend further. Okay, and this projectile, which has nucleons in various states, goes past at high velocity past a target, say beryllium-9 or carbon-12, and nucleons are removed from the surface. Okay? Another way of looking at this is the target looking in the beam direction. This is the projectile coming towards me. The target sits here somewhere in the surface and occasionally will move either a neutron or a proton with some probability, and that probability will be determined by how big the wave function is out here near the surface for the species of nucleon and the angular momentum of the state for which the particle is in. Okay? But I hope it's clear, just looking at this cartoon, is that sometimes the target will remove nucleons from the Fermi surface like this, in which case the object will be left in the ground state. Sometimes it'll remove one of these guys which is in a more strongly bound orbit, and then this will be left in an excited state. Okay? So seeing a gamma ray after the event and seeing a de-excitation gamma ray is probably indicative that you've removed nucleons from more well-bound orbitals below the Fermi surface. Okay? And so it gives you information about what is happening in the structure of this system. Okay, but what we see I think what this cartoon will also convince you of, what we're going to look at is what the wave functions are doing at the surface. Okay? I think it's fairly clear that if this target nucleus, if the impact parameter here, B, gets too small, this guy is just going to collect a dozen nucleons. It won't take just one out, it'll just go smash and rip out a whole bucket full of nucleons, and that will not be a one nucleon removal reaction. Okay? The likelihood is that when you find just one nucleon, it means that the target and the projectile have interacted with each other just in this diffuse haze of stuff around the surface and beyond the surface of the nucleus. So we're expecting a surface-dominated nucleus. If that is helpful to us in formulating the reaction theory, so be it. But we expect that we're going to be surface-dominated in this reaction channel where we're looking for events where just one nucleon has been removed. Okay, so again, if we put those together, what it really means is we're going to be probing the densities here somewhere around the surface. Okay? Okay, the other thing one measures is the momentum. Okay? The momentum distribution is a very key observable in terms of understanding the orbital angular momentum nature of these states of the nucleon. So here's my cartoon. Okay? So what we've got is a core of nucleons in this A+1 body projectile, and A and the other one, which is going to be removed. Okay? And in the center of mass frame of this particle, so if I go to the rest frame of the projectile, at any instant, if this guy has a momentum k in that direction, this nucleon will have an equal and opposite momentum in that direction. Okay? Simple momentum conservation. Okay, so in the projectile, whatever momentum this A-body system is carrying is representative at that instant of time of what the momentum being carried of this nucleon is. Okay, and so what happens then is that if this is just the projectile, okay, if instantly the target comes along at 0.6 of the speed of light or whatever, the target goes whizzing by and instantly takes that one out. Okay? Then this guy, whatever momentum that one is carrying a memory of what momentum that one was carrying. Okay? So that's the way the knockout reaction is thought to work. In the rest frame of the projectile, we've got some momenta. Then we instantaneously, suddenly, we just wipe that one from the scene. And so this momentum added to the momentum that it has in the forward direction will yield some final momentum for this object here. Okay? And this momentum will carry information about the instant momentum this had, which is just a fixed number. It's whatever momentum the original particle was carrying down the beam, and this object will be carrying A over A minus 1 of that instant momentum, okay, minus that guy. Okay? So by interrogating the momentum of this, we learn something about that, and the momentum of that guy, the momentum components carried by this nucleon will be highly characteristic of the wave function of this system here. Okay, so this is, I meant to bring two apples. Okay, what do we expect for this momentum distribution? Okay, just think about it classically. Imagine we've got a particle here and a core, and they're bound with some angular momentum. Okay, I think I've got some apples over there. Maybe I should use the apples. Okay, so what we've seen is if I take this one instantly, we have some memory about what momentum this one was carrying in the rest frame of the projectile. Okay, so I'll ask you to consider, imagine that I've got two particles which are bound with a fixed angular momentum. Okay, now what happens oh, thank you so much. The core plus some flesh, the core and the valence particle. Okay? So if I say I'm going to fix the L, then these things are rotating with some angular momentum. Their masses are fixed, so that means some rotational frequency. Okay? Now what happens if this thing is weakly bound? What's the primary effect of weak binding? That. Okay? So if I want to have a fixed angular momentum of 1 unit, say, what happens? I have to rotate these through. And how fast do I have to rotate them? If they're further away, then a smaller angular velocity will generate the same amount, okay? If I bring them close together, because the separation energy is high, if I want the same unit of angular momentum, I've got to rotate them faster, okay? So apples are great, okay? Okay, so what I'm trying to tell you with the apples is that if this is in a bound state with a fixed angular momentum, then if the angular momentum, if the separation energy is small, these will travel relatively slowly, and so the momentum that the core fragment is carrying will be smaller. Okay? Whereas as the separation energy increases, they're going to get smaller, they've got to rotate faster, and so the momentum carried by this guy are going to be bigger, and the momentum distribution would be wider. Okay? So one thing we can say immediately is that depending on the separation energy of this pair of objects, I expect the momentum distribution to be wider or narrower, and if we've got a weakly bound system with low angular momentum, the momentum distribution should be very narrow. Okay, and looking at the other way, we can just interpret the thing the other way. If I fix the separation energy, so I fix the size, if it's got low angular momentum, then they're traveling slowly. If I want a high angular momentum state, then I have to rotate them faster. So once again, if I fix the separation energy states for the same separation energy and increasing angular momentum, the momentum distribution will be wider. Okay? So if I have beryllium 11, and I know that the separation energy of a neutron from beryllium 11 is half an MeV, I should expect a very different momentum distribution, whether that the bound state is an S state, a P state, or a D state. So the momentum distribution should be increasingly wider, depending on whether it's S, P, or D. Okay, that's the prediction that's the Apple prediction. Okay. Okay, so we can look at this in a purely classical way and understand what we expect the sensitivity that we should measure in a momentum distribution to do for us. Okay, so how can we calculate these rather inclusive processes? Okay, well, I'm going to go to these products of S matrices now that we had in the start. Okay, so I want to assume that we've got two particles that are bound in a ground state, wave function phi naught. Okay, and I want to work out, well, let's make this point. The S matrices we've got, we're at high energy, 100 MeV per nucleon, so the S matrices we're talking about are going to have a modulus squared less than 1. Okay, there's absorption going on, and so not all the flux that comes in is able to go out. There's absorption, so this is going to be true. Okay, now if I want to ask what is the absorption cross-section, okay, if I fire oxygen 23 at beryllium 9, I want to know the probability, the absorption cross-section, okay, which is the probability that I don't get oxygen 23 coming out the other side. Total absorption cross-section, okay. Now, so I would claim it's given by this expression here, okay. We're interested in the particle coming in this ground state, so there's a ground state either side. That was the structure we were talking about before. And 1 minus S core, S valence squared. What does that combination of stuff mean? Is my question. That's what we, okay. SC is the probability that the core comes out, correct? Probability amplitude. Modulus of that squared is the same thing as modulus SC squared, modulus SV squared. Okay, it's just complex numbers. Okay, and the modulus of SC squared is the probability that the core particle goes into the reaction and comes out the other side. Okay, this one is the probability the valence particle is also instant and comes out the other side. Okay, so that probability, that second term there, is the probability both the core and the valence particle emerge after the reaction. Agree? Yeah, okay. So 1 minus that quantity is the probability that either the core, the valence particle, or neither of them come out the other side. Okay, it's the probability that an absorption has taken place and one or both of these don't come out. Okay, because that is the probability that they both do, and so 1 minus that is the probability that one or both of them do not. Okay, So there's a little exercise here, which is on the example sheet for this afternoon. You may be able to see it just by looking at it, but if not, you can do it later. Okay, I can rewrite that probability 1 minus the modulus squared. I can write it, re-express it in 3 terms. Okay, that thing is the sum of this plus this plus this. Okay, so that absorption cross-section, I can rewrite, or that absorption operator, shall we say, that stuff with a bracket there, I can write as a sum of 3 terms. Okay, in this one, tell me what happens here. The valence particle comes out, but the core does not. Okay, so that I'm not interested in that. That's not a 1 nucleon knockout experiment, right? I want the core to come out, but the nucleon not, right? I want the nucleon to be removed. Okay, so that guy is not something I want to calculate. Then there's another term involving this one, where the core comes out and reaches the detector, but the valence particle does not. Okay, fine. And then there's the other one, which must be there, that neither the core nor the valence particle comes out, and that's a more complicated absorption event. Okay, so the bit of the absorption cross-section that we want, if we have particle coming in and we measure the core fragments going out the other side, is this one, okay, where the valence particle undergoes an absorption event, interacts strongly with the target, and there's an inelastic scattering, and the core survives and comes out the other side. Okay, so this is saying that if I want to calculate using these iconal methods what's called the stripping term, this idea that oxygen 23 comes in and we observe oxygen 22 coming out the other side, this is the thing that we would compute. Okay, and we can do that provided we have a ground state wave function and we can got some optical potentials so that we can calculate the S matrix element to calculate these things here. Okay, so you see the game. I hope you see the game we're playing. Okay, we can identify, based on these expressions for very general cross sections, we can identify the pieces that correspond to certain sorts of physical interaction and the detection of certain of the fragments and relating to experiment. Okay, so that's the picture. Okay, there's an S matrix element between 1 and the target. There's an S matrix element between the core and the target. Due to this interaction, there is a bound state telling me about the quantum numbers of this, and the claim is that if we calculate this guy, then we can compute the cross-section for observing this guy coming out, that nucleon having been removed with those quantum numbers. Okay, well, there's another way of the nucleon being removed, and that's the one that Antonio and we have been talking about with CDCC, etc. Okay, it's possible that the neutron coming in with 100 MeV per nucleon does not smash into beryllium-9 or carbon-12 and have some inelastic event, but actually the neutron comes in and there's a breakup event, and the neutron goes out and the core goes out, having been excited by the optical potentials. Okay, there's like a CDCC calculation. So this is a much less violent event, where you have an elastic breakup of the projectile, and this will be important, of course, if the projectile is very weakly bound, such as beryllium-11. Okay, so if we want to treat this one, then let's just go through this rather quickly. So this is called diffractive dissociation, elastic breakup. So you can calculate this term with CDCC if you want, but this is the way you would do it with the iconal theory. Okay. So this is the amplitude, this is S for the valence particle, this is S for the core, and as we've seen, what we want is to come in the ground state, and we would like the probability amplitude for ending up in a breakup state of a given K. I don't care which state, final state, scattering state we end up in, so we can integrate over all K, integrate over all final breakup states, and that'll give us what's called the diffractive cross-section. Okay, so once again, we've got the composite object, so we've got the product of S matrices sandwiched between wave functions. This gives us the amplitude for this process. We modulus square it to get a cross-section. We have to integrate over all impact parameters, and we integrate over all possible final states, which the thing might break up to. Okay. Now, we say we don't usually calculate it in this way. Because I have an integral over all final states, I assume people have met completeness relationships in quantum mechanics before. If I sum over the complete set of eigenstates of a Hamiltonian and put their kets back to back like this, then I get 1. Okay? And so I've got a complete set of scattering states. This Hamiltonian will also have some bound states in general. And so there's a completeness relation that allows me to relate this integral over all scattering states to 1 minus certain integrals over bound states, the bound states of the Hamiltonian. Okay? If you haven't met that before, then don't worry about it. But it means that this calculation for the elastic breakup piece can be recast in terms of a different expression involving only bound states without the need to do this integral over all states in the continuum. Okay, so that's there as well. Okay, so I'm just really indicating there are 2 processes that can happen. This one comes in, smashes into that, excites this, and something nasty happens, or it can come in and one of these elastically scatters from this, and this guy simply breaks up, and the neutron, the core and the neutron go out. And you can't distinguish between those experimentally. They both result in a core fragment going forward, and so this diffraction cross-section and that earlier stripping cross-section need to be added together to give us the final cross-section. Okay, so what's next? Okay, so I hope I've given you an idea about how you translate these pictures, these cartoons, into expressions which reflect the physics. Okay, and the important thing that I've been doing is that we've always got these products coming out. It's always the products. The fact that we got a pair always is appearing this product of S matrices that appear in these equations. Okay, now I think I need to revisit this stuff, okay? Because I don't want us to take this bound state thing, two-body bound state thing too seriously. We should always remember when we talk about this, as I said, we're really talking about real A+1 body nuclei, anti-symmetrized, etc. So let me just link up with what we did earlier on last week. Okay? So let me remind you this transparency. So I'm just showing you some transparencies we've seen before. Okay? So as we've just said, we've just been dealing with a sort of potential model where we define a normalized bound state with some quantum numbers, but as we heard in some detail last time, what we're really talking about here is our overlap functions here when we need spectroscopic factors. Okay? Remember this stuff? You remember seeing it before. You may not remember the detail, but you remember the arguments, I think. Okay? That really, if we want to talk about this relative motion wave function, we should start from this point and recognize that there is an overlap function which has characteristics of a normalized bound state, but won't be a normalized state. There'll be a spectroscopic factor coming in. Okay, so here's my laying the things bare. I've written the equations as if the projectile is a two-body bound state, but of course the nucleon, and let's call it a neutron to be definite, is removed from a many-body wave function as we discussed last time. Okay? And if you remember, the key thing was that there was an assumption that the removal reactions, in this case, perturbs the motion of just the nucleon without affecting the other A coordinates of the nucleons that left behind. Okay? So in our case, the operator that is removing the nucleon, for instance, in the stripping term, is this guy, right? That's the thing that sits in the matrix element, and this is the thing that is responsible for inelastically removing the nucleon from the thing. Okay, so if this is the operator, then indeed, as we had last time, if I start with the original nucleus and I end up in the nucleus with one nucleon less, this operator, which depends only on coordinates of particle 1, need not stay in that matrix element, can come outside, and we end up with this overlap function, which is a function of the single variable of nucleon, which I've labeled number 1. Okay, so where I really should have started from is that what I'm trying to do if we're moving a neutron is that I've got n identical neutrons in a many-body wave function. Okay, the many-body wave function is this thing in general. It's got spin A and projection alpha. Okay, and I need to calculate something like this, really. Okay, there is the n. The cross-section, I've called the nucleon 1, but of course there are n identical nucleons, so there must be, the cross-section must be n times this, okay, because there's n identical neutrons in the target, and I could remove any one of them. Okay, so this is really where our starting point should be, rather than this simplified guy that we had over here. Okay, so I'm reinterpreting this stuff and trying to show that this simplified thing is indeed the thing we can do, provided we're aware of the spectroscopic factor. Okay, so what can I do with that? It's a mess, isn't it? Okay, so this is the removal. This is the absorptive operator for the neutron, and this thing here is just the collective S matrix for all the remaining particles which are not nucleon 1. Okay, so everything that's in nucleon X here is I've lumped together into this S matrix here. Okay, because this object X has to survive. It has to come out the other side. Okay, so this is the product that I want. Okay, so this is we need to work out, and I say this is completeness again. Okay, if I really have this nucleus X, which is a complete set of states, I've got all these excited states of the nucleus X. If they're eigenstates of a Hamiltonian, then there's a completeness relationship and says that this object, where you put the bra and the ket back to back and sum over all the states, is equal to 1. Okay, it's a unit operator. Okay, so you may not want to concentrate on all the details here, but say, what I'm going to do is that's the expression I would like to work out. I can split up this thing, which is modulus of Sx squared, into an Sx and an Sx star. And if I want to, I can put unit operators in any place I like in here. Okay? You can always include ones. Okay? And so formally, I can put a complete set of states into various places here. Okay? And there's a proviso here. Okay? So let's include all these possible states of B as complete sets at these different points. Okay? And if we assume, remember what our basic assumption was, that what I'm going to do is remove nucleon 1, but the operation does not change the states of the nucleons that constructing B. Okay? So if we assume that this Sx here does not couple or excite the states of X, then it means whenever I have something like this with an Sx sitting between states of X, it's diagonal. Okay? This is the statement that Sx does not excite a couple different states of B. Okay? All right, so if you do this, and I say it's a very simple pen and paper exercise to make these substitutions and to simplify using this approximation, then this object that we wanted to start out with reduces to an equation which involves only the overlap functions here on the outside. So something looking very like our bound state that we were working with originally. The absorption operator for the neutron, and this operator SB, which is Sx sandwiched between this wave function. Okay, so this is the elastic scattering S matrix of the object B, nucleus X, from this is the elastic scattering S matrix for this object X with the target nucleus. Okay. At the end of the day, as I say, what we do is calculate the earlier simple expression. But I think we need to always bear in mind that we're making a many body to a few body reduction. Okay, and our bound state that we're talking about is always related to an overlap function of the sort that we've got here. Okay, so the additional thing we need to connect with what we were doing last week is that, of course, this overlap needs to be consistent with angular momentum conservation. And if you'll remember, we defined the spectroscopic factor connecting the overlap to a normalized single particle function. I'm not going to do this again. We did this last time. Okay, and putting that together with what we've got up here, we end up with this final expression down here, which looks very much like the simple bound state picture that we had before. Okay? And what it's saying is that there is a spectroscopic factor for populating the given state B from the initial state A by removing a nucleon with a particular set of quantum numbers. So this weights the thing, the transition. And this is the stripping cross-section for removing a particle from nucleus A, forming nucleus B, removing the nucleon from this normalized single particle wave function here. Okay? So this looks essentially like our initial simple model. Okay? And the difference is that we can populate several final states, and this cross-section has to be multiplied by the spectroscopic factor for this particular transition. Okay, so we're going to need, to work out such a calculation, we need a small number of things. I need a potential, because I need to generate the S's. I need a bound state wave function, because I need to describe these states here. Okay? And I need a spectroscopic factor in order to calculate this cross-section when I've got it, to compare with the experimental cross-section. And we've discussed all those things now. Okay? We've discussed all those ingredients, and we should be able to put all those ingredients together. Okay? Just to remind you, if we're talking about independent particle models, we had some very specific expressions for what these spectroscopic factors were. Okay? And you remember, if I had given orbital J with a given number of nucleons in it, and I was going to remove one, we were able to calculate the spectroscopic factor. Remember we did it for the calcium isotopes, and we got a staggering. Okay? So perhaps you can remind me, if this shell is full, what is the spectroscopic factor? If I have an orbital J, which can hold 2J plus 1 nucleons, what is the spectroscopic factor for taking one nucleon out of a filled shell? How many are there? It's a filled shell, so in our language that we had last time, it's seniority 0, or everything is paired up to angular momentum 0, and it's an even number, and the fractional parentage coefficient, when we had n particles into an orbit coupled to 0, and that n was even, was 1. Okay? So it meant the spectroscopic factor was the number of particles in the orbit times this number here. Okay? So let's ask again. If I've got a filled F7 halves level with 8 nucleons in it, and I'm going to take one out, what's the spectroscopic factor? Shout. 8. Okay, 8. Okay. There was the other limit at the other end. If I've got a shell which has only 1 nucleon in it, remember? That's this parentage coefficient. If I've got n particles in an orbit and n is odd, and those coupled to j, okay, then I remove one and I get naught on the other side, then it's this formula. Okay? But I think you can see if you've got just one particle in the orbit, n is 1, and so you look at the right-hand side of this, you've got n minus 1, which is 0, and so you've got 2j plus 1 over 2j plus 1, and this number is equal to 1 also. Okay? So if you remember, when we started talking about this, we had the two limits. So if we've got only one particle in the orbit, the spectroscopic factor is 1. If I've got the orbital filled, the spectroscopic factor is 2j plus 1. And then in between, more complicated things happen, and it zigzags back and forth. Okay? But at the ends, it's very simple. Okay, so we can use that in a moment. Okay, so as I said, another thing we need, because we're dealing with systems for which we can't look up optical potentials from the literature, a standard way of computing, for instance, oxygen 23 on beryllium 9 says that I need a nucleon, beryllium 9, and I need an oxygen 22, beryllium 9 optical potential. Okay? Now, a standard way of doing that at high energy is to use a double folding idea. Antonio has talked about this, Philomena has talked about this. So this involves computing densities for nucleus A, compute the density for nucleus B, and then you do an integral which involves the two densities and an effective interaction between pairs of nucleons. Okay, and up at the energies that we're talking about, one can parameterize such effective interactions reasonably straightforward. I'm not going to delve into this. This is an effective NN force which we can use for these sort of calculations. Okay, so once again, if these are systems which you can't look up the answer, we can calculate the densities using the machinery we've got. We can use a force between two nucleons, and so we can compute this optical potential. And once we've computed the optical potential, we can calculate the S matrix from it. Okay, so this is that's what it looks like under the bonnet. Okay, so if you don't know what the potentials are, we can use either the double folding model if we've got nucleus-nucleus, or we can use a single folding model if we've got nucleon-nucleus. And say what I need to do these are densities for these guys, density for this guy, and an interaction between these two, as I wrote on the previous stage. Okay, so we have to use theory to calculate optical potentials, usually for such systems at high energies. Okay, let's do an example to see what's needed. Okay, so what's involved then in doing a realistic calculation? I think we've discussed all the ingredients. Okay, so let me return to this example that I've been throwing at you now and again through this talk. Okay, let's imagine oxygen 23, removing one nucleon clearly to produce oxygen 22. Okay, so this is the first order shell model scheme. So where do we find the last neutrons in oxygen 23? It's clear what the protons are doing. It's 8. It fills the P shell. Okay, and then we've got 15 neutrons. So 8 of the neutrons go into these levels here to fill the magic number 8. And then what happens? We've got 7 left over. How many can we put in D5 halves? 6, which leaves 1 left over, and that one the last one will go in 2s a half. Okay, so our naive expectation is that oxygen 23 should be a half plus ground state with the last neutron sitting in this orbital here and that orbital being filled. Okay, so we should be able to tell based on the previous transparency then. I've got 1 nucleon in 2s a half, so its spectroscopic factor is 1 particle in the orbital? 1. I've got a filled D5 halves, so the spectroscopic factor for taking a nucleon out of D5 halves is 2J plus 1, where J is 5 halves, is 6. Okay, so we need that ingredient. Okay, there's 6 nucleons can be removed from here, and there's 1 that can be removed from there. And so if I remove a nucleon, I'm likely to pick up combinations of both of those. So in a moment, we'll need to know those. Okay, so here on the right is sort of what we think is going on. Here on the left is again an encouragement to now and again run the Hartree-Fock just to see what it says is going on. Okay, now as we say, here's the Hartree-Fock. The neutrons has filled the P shell. I've just shown the top bit. And according to the Hartree-Fock, the P shell is filled. There's 6 neutrons in D5 halves and 1 nucleon in the S a half. It says the D5 halves neutrons are bound by about 6 MeV. These are units of 2 MeV each. And it says the last S-wave neutron is bound by what, about 4. Okay? But we know the separation energy of the last neutron in oxygen 23. Experimentally, it's 2.73. Okay, so this isn't quite right, but it's okay. It gives 4 instead of 3, basically. Okay, and but if we're going to do removal calculations, I need to know where that one is bound and the binding energy of these. And I don't know where the binding energy of these are experimentally. So let's take the value of the D5 halves here, that says that this level is bound at about 6 MeV. Okay, so this is one thing we need. Okay, we need to know at what separation energies to calculate the overlaps here. Okay, and that's our picture. Okay, so the likelihood is when oxygen 23 is incident at high speed on a beryllium-9 target, some of the time I'll remove this guy, leaving oxygen 22 in its ground state. Sometimes I'll remove one of these guys, leaving oxygen 22 in an excited state. And Obviously, some of the time I can remove these as well, but they're bound by 12 MeV, so these cross sections are going to be somewhat smaller, but you should calculate them. Okay, one should calculate them and add them on as well, but they will be smaller contribution. Okay, so that's a very naive expectation based on the experimental value for this separation energy and the Hartree-Fock positioning of this level here. Okay, so separation energy here, and we've discussed the separation, the spectroscopic factors, right? We had a communal session a couple of moments ago, and we've decided 1 and 6, okay, for that. Okay, and this is experimental levels in oxygen 22. Based on a naive expectation here, you might have thought that if you take a nucleon out of this guy, that costs 6 MeV. Taking a nucleon out of here costs 2.7 MeV, so the difference between those numbers would be naively the position of excited state in oxygen 22. Okay, so those values would give a state at what, 3.3 MeV? And there is a physical state at 3.2 MeV. Okay, so all I'm trying to say is if you look at what you know experimentally and look at what you deduce sort of experimentally and from theory, you get a sort of consistent picture of what is going on here. Okay, so in order to calculate the optical potentials theoretically, I need the new oxygen 22 density. Okay, if I'm going to do double folding and find the oxygen 22 interaction with beryllium-9, I need an oxygen 22 density. And so those I can calculate using the sort of process that you've had before. I've also put on there the density for oxygen 23. And that's the red curve. Okay, so why is this density for oxygen 23 and oxygen 22 showing this difference? Do you know? Which states of a nucleon contribute to the density at 0 radius? Which radial wave functions are non-zero at the origin? S states. Okay? Okay, so what's the difference between oxygen 22 and oxygen 23? That guy. Okay? That last nucleon sitting in a 2s state. You can see directly that in the Hartree-Fock calculation, that's giving rise to this extra density near the center of the nucleus because it's an S state, and that's where S states don't vanish. Okay? The P's and the D's, everything else vanishes. So when you add nucleons in an S state, you see an enhancement of the density near radius 0. Okay, so that's showing you just what you would expect to happen by adding an extra neutron in an S state. Okay, so that's one thing one can calculate. All right, so that's that. That's one ingredient. We need the oxygen 22 density. And if we're going to compute the cross section, and the target is, I've been saying beryllium-9, the target in this case is where there's a measurement is carbon-12. Okay, so there is a measurement at 72 MeV per nucleon on a carbon. Sorry. I'm not sure there is a measurement for this one. Is there a measurement for this one? Yes, there's a measurement for this one, made at ReChem at 72 MeV per nucleon on a carbon target. Okay, so I've tried to put together the things we need. Okay, we need bound states for this guy. We need a bound state for this guy. These are their separation energy. These are their quantum numbers. I need a density for the oxygen 22 and a density for the carbon 12 in order to calculate the optical potential using double folding. There's the effective nucleon interaction that goes into the double folding calculation. Okay. This is what the single particle wave functions look like. Standard geometry, 1.25 radius, spin orbit force of 6 MeV, a diffuseness of 0.7, and nothing special there. This is the D wave bound by 6 MeV. This is the 2s1/2 state. It's got a node because it's the second S state, and this is what the radial wave functions look like. Okay. So given that, we can calculate the cross sections. Okay, but before we do that, this is the object that's responsible for stripping a neutron out of oxygen 23. Okay? Let's remind ourselves this is the absorption probability for a neutron as a function of its impact parameter. This is the transmission probability, the survival probability for the mass 22 residual nucleus as a function of its impact parameter. And this is what they look like as a function of their impact parameter. Okay? This factor is here. Okay? So in order that the neutron is indeed absorbed and removed from the oxygen 23, the neutron would like to be at small radii. It would like to overlap the target, and eventually, as you go to larger impact parameters, it misses the target, and then there's vanishing absorption probability after some impact parameter. Okay? This is the survival probability for the oxygen 22. Okay? If it comes too close an impact parameter to the target, it has zero probability of surviving. Only when the oxygen 22 grazes the nuclear surface, so its impact parameter becomes reasonably large, does it go past the surface and not get absorbed. Okay? So given this information, you can see that there's going to be a geometrical selectivity here. Okay? In order that the neutron is removed but 22 survives, we're going to have sort of configurations that look something like this, where the neutron gets close to the target, enters the region of small impact parameters and gets absorbed, whereas the core stays far at some significantly large impact parameters from the target and so gets by unmolested. Okay? So I think you can see that this factor and this factor, when you combine them, really do mean that the reaction is going to be dominated from sort of configurations that look like this, where the neutron is silly enough to be on the side of the nucleus near the target and goes smash, and the remaining nucleons are just sufficiently far away that they go whoa, and the target goes by. Okay? But I think these pictures are useful in understanding what this is telling us. Okay? Because it is really a simple picture where you're looking at grazing collisions. Okay, for a different case then, when you put those two together, you can ask as a function of the impact parameter, the center of mass of the object, and this is for beryllium-12, it's the picture I had available. What is the probability as a function of impact parameter that the stripping and diffraction processes will happen? And there they both are. And you can see that when the impact parameter is too small, you get no probability of a one nucleon removal reaction. More complicated things happen. As the impact parameter goes bigger, then you get near the surface, and suddenly this guy is able to go by, and this guy is able to interact, and you get a peak. And the dominant reactions are happening near the surface at something like the touching radii of these two particles. Okay, we've done the spectroscopic factor, so I don't have to bother you with this anymore. What we learned by looking at that figure is that the spectroscopic factor for S1/2 was 1, and by popular agreement, we also agreed that the spectroscopic factor for a 1D 5/2 was 6. Okay, one end of the shell, the other end of the shell, whatever. Okay, so now, let's say using the code that you've got, we can calculate. I hope you'll say one thing you can do is try and reproduce these numbers yourself, okay? Based on these tools you've got, densities, you can calculate the folding potentials, you can calculate the S matrix, you can put these things together to compute these cross-sections, okay? So if you do that, and if we do it right, and there are far fewer buttons to tweak than in Fresco, I can assure you, okay? Far fewer buttons to tweak. So if we calculate the cross-section for removing a neutron from oxygen 23 from this S state, one calculates a cross-section of 72.7 millibarns. Okay? Take my word for it. It's a big cross-section. Okay? It's a big cross-section. It's a big cross-section because it includes, it's very inclusive, it includes many channels. Okay? Now these D-wave ones are more well-bound, so the cross-section is smaller. Okay? So instead of 72, the cross-section for removing one of these nucleons is 28. Okay? However, the spectroscopic factor for the D5/2 is 6, and the spectroscopic factor for this one is 1. Okay, so if I want to work out the cross-section for removing one or the other, the cross-section for removing a neutron is 6 times that for the D5 halves, because the spectroscopic factor is 6, and 1 times that for this one. Okay? And so you get 242 millibars. Okay? I haven't fiddled the numbers, okay? Just densities, just bound states, just separation energies, okay? And it predicts that the cross-section you would expect would be 242.5 millibars. And as I say, this measurement was done some time ago at RIKEN, and the number was, pity about the error bar being so big, right? But 233.37, so for free, without using the independent particle model, realistic descriptions of what the separation energy is there, what the active nucleons are, you get very close to what is measured. Okay?
Do we find a relation between this absorption cross-section and geometrical cross-section?
Well, we're not working out the entire absorption cross-section. As I say, there were several terms in the absorption cross-section, right? And we kept one of them. We kept the part of the absorption cross-section where 22 nucleons came out and 1 nucleon did not. There were other parts of the absorption cross-section which contained. Okay? You remember that step?
Yeah, I know. But
Okay, so we're only calculating part of the absorption cross-section,
yes, but not the whole cross-section, not the whole.
not the whole one. Okay?
But do we find any relationship between geometrical cross-section and absorption cross-section?
Well, I'm not sure what you mean by geometry. What I'm showing you is that this magnitude of this cross-section is very sensitive to which nucleons are active and which orbitals are filled and how filled they are near the Fermi surface. Okay?
Does it mean
If
it has nothing to do with the geometrical?
not directly, I don't think it is. It's related to separation energies and more subtle things than just the geometrical cross-section. Okay? If I added one more nucleon here, such that I put another particle in this state, then this level would be filled and the spectroscopic factor would be 2, right? And so this cross-section I would expect to increase by another 70 millibars, just from adding one more nucleon in the SR half. And this is, you saw the density for oxygen 23, and if I calculated the density for 24, the physical size isn't going to be significantly bigger to increase this cross-section geometrically by that amount of cross-section. Okay, so you can see that if I calculated oxygen 24 now, by putting another neutron in here, I can make a prediction directly that I would expect the cross-section to be 242 plus 73, be 300 and whatever. Okay, and similarly, if I was looking at oxygen 22, where that guy wasn't there, we'd expect this to be 70 millibars less. So these are much more massive changes than the changes in the nuclear size that have been the 8 to the 1/3 that are being induced by just changing one nucleon from 22 or 23.
Okay. In conclusion, the absorption cross-section in this case just tells us about only likelihood of absorption of the transmission. So
I think the total absorption cross-section will be much more related to what you're talking about, the geometrical aspects. We're just looking at an individual part of the absorption cross-section, okay? And the relation of this one to geometry is not so obvious, okay?
it's not obvious.
It's not. I don't think it's so obvious. I think looking at this example, you should be able to see that you can get really quite large changes in cross-section for rather small changes in the structure, which is why it's rather nice, because this is a sensitive indicator of this. Okay, so this measurement is inclusive. Okay, but so what our calculation would also do here is that we would say that number, which is 70 millibars of this cross-section, we think, based on our calculation, would lead to oxygen 22 in its ground state. Okay? But the majority of this cross-section, which is 6 times that, which is what? 6 threes? 170 something. 170 millibars of this is actually involved with removing one of these particles and will populate oxygen 22 in an excited state, for which we should see an accompanying gamma ray, for instance. Okay?
So I should have considered separately
It would be, well, say, in the early days of these measurements, one didn't have the gamma ray detection to look at the final states. People now recognize the importance of doing that, because if we can measure these two pieces individually, then clearly we learn much more about the occupancies of these two states near the Fermi surface than if we've just got an inclusive sum. Okay. Okay, so we're running up to lunch. So what I've tried to do there is to give you the underlying theory, try and convince you that we've got these simple representations of bound states, but they're realistic descriptions of the overlaps, provided we take the spectroscopic factors into account. Okay, and that I'm not claiming this is the last word. Okay, I'm just showing you that cross sections of the sort that you measure come out very naturally when you use sensible physical inputs. Okay. All right, momentum distributions. This is what we're calculating, slightly different notation because I took it from another paper. Okay, but this is our stripping cross-section involving elastic removal of a neutron. This is the core survival probability. This is the state of the removed nucleon. Okay, we can rewrite this. You can actually change the variable of integration. Instead of integrating over the center of mass impact parameter, it's possible to change the variable of integration in this integral. You know how to change variables of integration, so that we actually integrate over the neutron impact parameter instead of the center of mass one. It's just a simple transformation of coordinates, in which case you can write the stripping cross-section like this. Okay. Now, I want to play this trick again of completeness. Okay. This is the cross-section for any momentum of the final state fragment. By writing it in this form and then using this trick again and putting a complete set of states in here, I can decompose this cross-section into the contributions from different values of momentum of the final state fragment. Okay? We make this inclusive cross-section differential with respect to this momentum by putting a complete set of states and seeing how this integrand depends on the momentum. Okay? So don't worry about the technicalities, but you remember when we started we talked about the apples and the momentum distribution associated with the bound states. We can do that by taking our expressions and doing a theoretical insertion here to make this a differential so that we can look at the cross-section as a function of the momentum of the fragment. Okay? And as you might see, there's the bound state, there's SC, and once you put in the set of plane wave states, what we have is a Fourier transform here of S times the wave function and the relevant momentum. In other words, we're projecting out of this physics what the momentum content of the wave function that's being probed is. Okay, so that's taking it one level further, where instead of integrating over, okay, this guy does not depend on z. Okay, this is just a function of impact parameter, doesn't depend on a z coordinate, so this can come outside the integral. And we can then do the integral explicitly with respect to z as a z component transform of this, and that's what's sitting up there. Okay, so I want to show you some results. Okay, so the calculations are of the sort that I've just done, and I don't know if you can see the lines on here, but this is beryllium 10 resulting from a neutron having been removed from beryllium 11. The red points are experimental data. And this is the momentum distribution extracted from the data in the rest frame of beryllium 11. Okay, and there's three lines. The blue one is what you get if you assume the apples in a relative S wave with a given binding. Okay, so what we got here is fixed binding, fixed separation energy, but different values of orbital angular momentum. Okay, and what we saw was you expected the distribution to get, for a fixed separation, a fixed size, as the angular momentum goes up, I've got to spin this thing faster and faster, and so the momentum components become greater as the orbital angular momentum increases. And that's what this is showing. Okay, that's the momentum distribution if the neutron was in an S state. The dashed curve here is if it was a P state, and this one here is if it was in a D state. Okay, and so this is spectroscopy. Okay, this is a very nice confirmation that the last neutron in beryllium 11 is indeed spending most of the time in an S state with respect to beryllium-10. This is a similar, won't do this one as well, this is a similar discussion for carbon-15, and there's an exercise this afternoon if you want to reproduce these guys. Okay, so that's just probably clearer. I should have shown this one and thrown away the previous one. That's the same picture as on the previous slide. Okay. If you remember what the issue is here, if you look at the normal shell model scheme like this, and you ask which state you would expect the last neutron in beryllium-11 to be, this is the normal shell model scheme. Beryllium-11 has 7 neutrons, and if you put them in the normal scheme of the shell model, you would expect the last neutron to be in a p state. Okay? Whereas it's manifestly clear from the data that the last neutron in beryllium-11 is not in a p state, it's in an s state. So what we're seeing here is direct experimental evidence of the level inversion, and that state that would normally sit up there is in fact come down to below this state in physical beryllium-11. The s state is the last bound state of the neutron. Okay, so this is a very nice case, and you've got everything you need based on what we've discussed this morning to calculate those yourself if you would like to do so and see that dramatic dependence upon the L value of the bound state wave function. Okay, and this is our other example, the oxygen. Okay, remember, we can remove from an S wave with a spectroscopic factor of 1 or remove from a D wave with a spectroscopic factor of 6. This is the momentum distributions associated with that 240 whatever millibarns I showed you a moment ago. So if you did do an exclusive measurement where you measured the cross sections, 70 millibarns going to the ground state, those ground state fragments should have this momentum distribution. The residues that come out associated with the gamma ray, because we've populated an excited state, because we've removed a particle from d5 halves, would be expected to have this momentum distribution. Okay? So once again, this comes out of the same calculation that gave you those cross sections a moment ago, and you have everything you need if you wish to try and compute those cross sections and these momentum distributions, which are predictions. Okay? These are predictions about what you should measure if you go away and measure oxygen 23 neutron removal at 72 MeV per nucleon on a carbon-12 target. Okay, so I'm going to skip this, but you can look at this yourself. There is sensitivity in the momentum distributions to the projection of the angular momentum of the orbital. Okay, let me just indicate this way. Okay, I'm taking a nucleon out of some single particle state. Okay, then I've got my core and I've got my nucleon, and they're in some single particle state. Now if the beam is in this direction and the projection of the angular momentum of these two is in that direction, which means basically they're orbiting in this plane, okay, then these will have a maximum orbital angular momentum projection on the beam axis. Okay, the beam is there, and I happen to be in the substate of the bound state where they're orbiting in this plane. They'll have a large projection of angular momentum in that direction, but essentially no motion in that direction. Okay, so the component of momentum of these guys in that direction is rather small, and so that's the situation. Looks like this. Okay, if this is a large M projection, the particles are basically orbiting in this plane, and so they have minimal momentum in the beam direction. Okay? Whereas if they're orbiting in this plane, so that the projection is at right angles to the beam direction, they'll have large components of momentum in the beam direction. Okay? So that follows through to an expectation. I mean, once again, these are calculated using the codes we've got here. If the projection is like this, and the orbit is like this, and this is the beam direction, then clearly there's a very little momentum in this direction, and so the momentum distribution is rather narrow. Whereas if you're in a projection with a very small value with respect to the beam direction, then the particles are moving in the beam direction, and then the distribution, the blue one there, is rather wide. Okay, so there's also associated effects on the momentum distribution due to the substates, and of course when you actually do the calculation, you have to add all these up because we don't have any measurements yet which allow us to look at these contributions from these original substates. We'd have to have angular distributions of gamma rays or something in order to be able to determine an axis to be able to do that. Okay, so there's some codes on the website as usual, and that's takes us sort of up to lunch. Okay, so what I've tried to do this second half this morning is to tell you how nucleon knockout are calculated. What we need is a bound state wave function, which really means an overlap. Okay, we need iconal S matrices that we talked about a lot in the first past, and implicit, we didn't say it again, but we're carrying through the machinery from the first part this morning. So whenever we have a composite object, we're making the adiabatic approximation in writing down this thing with the product of S matrices. Okay, so that's understood that we're making this frozen approximation and that we're at high enough energy. Okay, I've tried to show you the momentum distributions via the apples. Momentum distributions, and yeah, okay, we can calculate those. They're sensitive to the orbital angular momentum value of the nucleon, and so they allow you to do some spectroscopy and learn about what the physical states of nucleons in the surface of exotic nuclei are. Okay. The final thing was that unfortunately for many of the systems that we're interested in, we can't look up optical model parameters, and so if we're going to generate realistic S matrices for oxygen 22 and carbon 12, I need to build in the proper sizes of these guys, etc. And one way of doing that reasonably naturally is to calculate the density of this, so that the radii of these things have the right size, and then compute the optical potential theoretically with a double folding, for instance. Okay, and it'd be nice to have all the optical potentials in a table, but we don't have to. So we have to make a mix of experimental values, theoretical values, in order to put a consistent picture together to calculate what we need. Okay, and I bet that's the last one, isn't it? Yeah, fantastic. Okay, so happy to answer questions, but I hope you can see there's lots of opportunity there for exploring these things, and I know some of you are interested as thesis projects in these things, so I'm happy to discuss it further with you after lunch.